Hello, my name is Bo Lark, and this is my Lab 2 video. A brief introduction. The objective of this lab was to create a computational model of the magnetic field produced by a bar magnet, and to also determine the magnetic dipole of the bar magnet, as well as the distance-dependence relationship of the bar magnet. The importance of the lab was to apply and conceptualize the formulas used to create the computational model. And a little preview of the results is that the computational model of this lab will provide a visual for what the magnetic field of the bar magnet looks like. Here are some key physics principles and equations. The magnetic field of a dipole points into the negative south and out of the positive north end. Dipole moment points from the south to the north, and you're going to need to know about superposition in order to calculate the net magnetic field. Here are some of the equations that we use. The most notable one on here is the second equation. This is the magnetic field of a dipole for when r is much greater than the separation distance. And then this little logarithmic function down here will be used to graph. Here's the experimental procedure. First, we had to download the magnetometer app, and then find magnetic north, and then place a meter stick on the east-west axis once we found magnetic north, and then locate the magnetometer on the phone by basically following these visuals below. Next, we were to find the distance along the meter stick where the magnetic field in the x direction was 20 microteslas, and they repeated this 2 more times and found the average of these distances. Printed this, and we did this for the following values. Also, we did this for off-axis data as well at a 45-degree angle by following the illustration below. Some of the assumptions that there was no magnetic interference from other electronics, and that the bar magnet acted as a magnetic dipole. Some of the observations that I made was that when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction, and that as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. Here's my calculations to find the dipole moment. Basically, here's the at the top of my calculations is my logarithmic function that I used to graph. As you can see, the slope of this function is -3, which is an experimental value, and it really should have been, or it's -3.8. The real value should be -3, so it's very close. And then I set Kr raised to the n equal to the magnetic dipole moment equation, and by manipulating that equation, I was able to find the magnetic dipole moment. Here's the data collected. The two most notable pieces of data that we'll refer to later in the lab is, first, we have the graph right here. As you see, the slope of this graph is -3, very close to what it really should be, which is -3.08. And we also have these two values circled in red, which we will test using our computational model to see how close we really got. Here's the actual code. As you can see at the top, we start off by defining some constants throughout, such as mu mag, and then next I go in to make a function to compute the dipole, the magnetic field of the dipole. And then next I set up all my observation locations, which we want to find the direction and magnitude for. Here I'm creating the arrows for these so you could see it in the computational model. Basically just cycling through the function with each new position, observation, location value. And then we do this again for the magnetic field at 45 degrees at the very end. And you can see here the values we took from the spreadsheet are also put into the code. Here's what the computational model looks like at the end. As you can see, the orange arrows are on axis, blue arrows are the perpendicular axes, and the purple arrow is the off axis location. What if I had instead laid the meter stick out at some intermediate angle with respect to Earth's magnetic field, how would my results have changed? They would have changed because the x component would either be greater than or less than the theoretical value, depending on where it's oriented, so basically greater than 0, although the graph would still look the same. And if I had 2 identical magnets instead of 1 and stuck them together, basically the magnetic field measurements that were made would be approximately twice as large due to the law of superposition. Here's my experimental findings. As you can see, my distance dependence relationship was very close to what it should be, which was -3. I found my magnetic moment by showing you the calculations before, and then my the analysis that I made on the off-axis location was very close to the experimental value. As you can see, the magnitudes were about 0.3 off when I calculated it, and a possible source of error were imprecise measurements due to human error and magnetic field disturbance from electronic devices. Thank you.